In this video, we will explain the intuition behind logistic regression. Despite its name, this is not a model that is used for regression. This statistical model is used for classification problems, especially for binary classification. And we cannot use linear regression for classification problems, and I will give you a brief explanation of why. If we draw the function of linear regression, let's say we have a data set and we have just one feature that affects the outcome. Let's say we have one feature, and that's the weight of person, and the outcome is whether this person is obese or not. So in the x-axis we have the weight, and in the y-axis we have whether this person is obese or not, and we can symbolize it with 0 and 1. Let's say this is 0 and 1, and weight, let's say 80, 90, 100, and we can place all of the people that are not obese here with empty circles, and let's say these are the people that has obesity. And here's the problem. When we try to use a linear regression, which is just a simple line, you can see that it is impossible to fit something like a line to these kind of data sets. And you can see that if we had something S-shaped like this, not like this, something like this. If we had a function that looked like this, it would be way easier for us to plug the features into that function. Then the outcome is between 0 and 1, and we put a threshold into it, and if the threshold is, if the outcome of the function is bigger than a threshold, we assume that this person has obesity, and otherwise this person doesn't have. So we have the feature weight, and we are looking for a function that when we plug the feature weight in it, it will give us a number between 0 and 1. So eventually it will end up with something called probability, and probability is between 0 and 1, and we have our weight function. So in this case we will have just one. This is the formula for the linear regression. Let's say we are just using linear regression, and the b0 and b1, they are the coefficients, and x1 is our weight. And when we try to use this, it will give us any value, because the domain of a linear regression is from -infinity to plus infinity. But this is one of the reasons why we can't use it, because we need something that will give us a value between 0 and 1. So and at this point we also need to introduce a concept called odds. Basically, when we have the probability of something happening, let's say this probability is the probability of an instance belonging to a class, and this is the probability of that instance not belonging to that class. And when we divide p to 1 minus p, we actually get the ratio of probability of this belonging to a class to probability of this instance not belonging to that class. And this is called odds. So we've done the first step, p divided by 1 minus p. But still, this function gives us a value between 0 and plus infinity, if I'm not mistaken. Yes, between 0 and plus infinity. But we need something that gives us any value, like linear regression, because we try to find something that the relationship is linear, the relationship between the weight. We assume that the relationship between weight and the probability is linear, but we cannot use a linear regression. So what we need to do is to map a function of a linear regression to a function that will give us between value between 0 and 1. So as you know that the domain of linear regression is minus infinity and plus infinity, we actually cannot do something like this. Because this function, this linear function, can give us any value, but this one will only give us values between 0 and plus infinity. So what we can do here basically is to take the exponent of each side. Sorry, not exponent. Firstly, we take the a logarithm of each side. Let's say, so ln is basically logarithm from base 10. And if we do the same here, and then what we can do, we can take add the function of exponent. Exponent is let's say we add exponent here, then we should also add exponent here. Then what happens is that the exponent and ln function, they cancel each other out, and what's left here is p divided by minus 1 minus p is equal to b0, the coefficients, and the features. So basically why we did it, no, we actually don't need to do this here. We need to just write ln. No, we don't need to write it actually. So here we have this function, and this function gives us a value between minus infinity and plus infinity. And our linear function also gives us values between minus infinity and plus infinity. So we can actually, this enables us to map the function of linear regression to this one. And what else can we do here? We will try to find p in this equation. We can see that, okay, we found a function that maps linear regression to this one because their domain is the same. What we can do here, we can take the exponent of each side, which is this, and then as you know, ln and exponent, they cancel each other out, and what's left here is that p divided by 1 minus p is exponent and these coefficients. And how do we find p here? We can write it as 1 divided by p minus 1, and this is and then we write we take minus 1 here, then what happens is that 1 over 1 plus yeah, we write it like this. And then we have p, we find p, which is, let's say like this is x. Then we have so finally p is this. What is x? X is a linear function of features and coefficients. So what happens is here is that we have features, we plug these features here, and then at the end of the day we get the probability. So let's say we have only weight. We plug the weight, which is x1. Then this function gives us a probability. And the shape of this function is exactly what we wanted at the beginning of the video. S-shaped. So we had data sets. We had data points like this, and our function, and this is also called a sigmoid function. Let's say we do this, because this function, the shape of this function is like this, and x is weight, and this is the probability. 0, 1. So we plug the weight, then we look where it is placed in this function, and then we set a threshold. Let's say this is 0.5, and if the probability is bigger than 0.5, we can say that this person is obese, otherwise this person is not obese. Logistic regression is used for binary classification, and it's used for interpretability, and because you can understand like which coefficients are most important and how we end up with a specific probability. But it's not used with huge data sets. And it's interpretable, and we also assume that the relationship between the features and the outcome is somehow linear. And if our dataset is small to medium, and we assume that the relationship is linear, and we want a model that is interpretable, then we can choose a logistic regression model.